Let's assume we have a block of wood of mass 3 kilograms, and we want to change the initial velocity of that wood. So it starts with some initial velocity of 1 meters per second, and we want to increase its velocity to 2 meters per second. And we want to do that over a time period of half of a second. What force must be applied to this block in order to do that? Okay, and let's assume that this is a block of wood on a wood surface. So we're going to be using a coefficient of friction. I want you to try to figure out which coefficient of friction we should be using. Pause the video. All right, I'm going to assume you did. If not, it's whatever. But we should be using this one, right? Because it's already moving. So we should be using the kinetic friction coefficient for this problem. So, when it comes time to calculate the frictional force, we should be using the kinetic friction. Okay, first things first, in any force problem, it's always a good thing to draw a free body diagram. So the free body diagram in this class is going to be with the dot. So here's the dot. Only one note hates the dot. So there's the dot, okay? We've got a force of gravity acting down on this thing, Fg. And that's just the case, right? Because it's on Earth, so it's got some force of gravity. We've got a normal force opposing that. These should be equal and opposite. I'm doing my best to draw that here. Bear with me. So the normal force. We've got a force that's pulling on the block because it's going to travel in this direction, right? And it's accelerating in that direction. So surely there should be some force pulling on it in that direction. That should be bigger than the friction force, right? So we're going to call this force pull, and we'll call this the friction force here. Let's call it friction force. Okay, they kind of look similar. I'll try to draw a little bit bigger in the next, but this is friction force. This is the force that we're pulling on the block with. Okay. We know that we want to accelerate the block in the x direction. So we know that the sum of the forces in the x direction are going to be equal to the mass of the block times its acceleration in the x direction, right? And that's equal to the forces, the sum of these forces in the x direction. So we've got the force we're using to pull, and we've got the friction force. Okay, the friction force, let's assume that the right is positive and the left is negative. So these are added together, but this one's negative. Okay, the friction force. We don't know what this one is. We could figure this one out, right? So we can figure this out. This one's unknown, though. So let's figure the friction force out. We know that the friction force is going to be equal to the coefficient of kinetic friction times the normal force. And we can figure out the normal force. It should just be opposite to the force of gravity, right? So the sum of the forces in the y direction are equal to 0, since it's not going to be accelerating in the y direction. And that's equal to the force normal plus negative force gravity, since we're assuming up is positive and down is negative, which means force normal is equal to force gravity, right? And we can figure out force of gravity. Force of gravity is, pause the video and try to remember it. Okay, force of gravity is m times g, right? Where g is 10 meters per second squared. All right, we're not going to plug numbers in just yet, so hold on that. That means force normal is equal to force gravity, so force normal is going to be equal to, that n got too high up. Let's try that again. Force normal is equal to mg, right? And that means that the friction force is equal to mu k times mg right? Mu k is the coefficient of kinetic friction. And we can plug that into there now, right? So we can find the force required to pull it. It's simply the mass times acceleration in the x direction plus moving that over, the friction force, plus the friction force, which I'm going to go ahead and plug in mu k for that. So plugging that in, and I've moved it on over to this side now, plus mu k mg is equal to the force required to pull it. So now we just plug in numbers, right? Because we know what the acceleration in the x direction is. I guess I should have calculated that right off the bat for you guys, but we know this. We know the acceleration in the x direction. It's simply the change in velocity over the change in time, right? The change in velocity is 2 meters per second minus 1 meters per second, and our change in time is 0.5 meters here, or sorry, 0.5 seconds. So that means the acceleration is going to be equal to 2 meters per second squared. So if you do 2 minus 1, you get 1, divided by 0.5, you get back to 2. You can plug that in to the a in the x direction, and let's just plug our numbers in now. So the mass is 3 kilograms, right? So I'm just plugging that in there, right there, okay? Sorry, loves to right click on this. I have to go back to the one note that's not 2016, but 3 kilograms times 2 meters per second squared plus mu naught k is 0.3, right? Right there. So 0.3 has no units, so don't worry about that. Times our 3 kilograms again, times g, which is 10 meters per second squared. Okay, crunching that number, you're going to get 15 newtons. So you'll get 6 newtons for this number, here, 6 newtons. And for this number, these 3, you'll get 9 newtons. I'm kind of running out of space here. For these 3, you're going to get 9 newtons. Add 6 and 9 together, and you get that 15 newtons is required to accelerate that block at 2 meters per second squared if we're already moving. Okay? All right. I will see you in the next one.